Okay, so we've talked about complete ionic equations, net ionic equations. Now it's time to give a little bit more definition to acids and bases and the subsequent reactions between them that are known as neutralization reactions. So a generic neutralization reaction is shown here, where we have a generic acid on the left and a base. And the reactive form water and some ionic compound, which we refer to as a salt. Now, it's called a neutralization reaction because the products that we end up with are neither acidic nor basic. They're neutral. So what exactly is an acid? You'll notice here that I've highlighted the hydrogen in the generic acid and the OH in the generic base, those two combining together to form water. Well, what is actually the definition of an acid? We've used this term, but maybe don't know exactly what it is for sure. Well, an acid is some substance that ionizes in solution to form the H+ ion. Now, hydrogen, the neutral hydrogen atom, just has a single proton in the nucleus, no neutrons, and then a single electron. If we lose that electron to form the H+ ion, all we're left with is the proton. And so we often refer to H+ ions as being protons. So if you hear that term proton or protic, we're referring to an H+ ion. Now, here are a few common examples of acids. HCl is probably the most common. It dissociates in solution to form the proton and the chloride ion. Nitric acid is also another very common strong acid. It also dissociates to give the H+ ion and the nitrate ion. And then in addition, we can also have acids that are known as polyprotic acids. The protic refers to the H+ ion, poly refers to more than one. So polyprotic acids are those that can ionize to give multiple H+ ions. A classical example of a polyprotic acid is sulfuric acid, where it can first ionize to give one H+ ion and then the hydrogen sulfate ion. But that hydrogen sulfate ion can then additionally dissociate to give another H+ ion and then the sulfate anion. So we also have to make a distinction between strong acids and weak acids. We made a little bit of a distinction when we were talking about electrolytes in terms of strong acids being good electrolytes, weak acids being poor electrolytes. And we need to make that same distinction here. So strong acids are strong electrolytes. They fully dissociate in solution. Weak acids are weak electrolytes. They only partially dissociate in solution. But how do we know what's a strong acid and what's a weak acid? Well, some of those details we will better understand as we get later into the course. But for the moment, we will just stick to a list of 7 common strong acids. These are the most common strong acids, and we will use these almost exclusively when we're talking about strong acids going forward. So those are hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, chloric acid, perchloric acid, and then sulfuric acid. Whenever you see these are our examples of strong acids. Now, what about weak acids? Well, I'll list a few common weak acids. It is, again, still a little difficult to identify when something is a weak acid or when it's not an acid at all. That might be a little bit confusing, but I'll point out a couple things that might be helpful with that. So here are some common weak acids: acetic acid, which we'd seen earlier, formic acid as well, and honestly, any other acid where you see this kind of this format in the formula show up, where you have COOH, that is indicative of a group that's known as a carboxylic acid. You'll learn more about that in a later course. But those are always weak acids. So we've got acetic acid and formic acid. Additionally, hydrofluoric acid is a weak acid, as is hydrogen cyanide. And then this last one, oxalic acid, as well. It's not written in the same format, although it could be with acetic acid. It's actually a polyprotic acid. This is also a weak acid. Now, what about bases? So on the base side of things, A base is some substance that accepts a proton or accepts an H plus ion that will react with it. So the vast majority of bases are something that produce the OH minus ion when they dissolve in water. And then that OH minus anion reacts with the H plus ion to form water. So the vast majority of all bases either contain OH minus in them, so they either contain the OH minus anion, as in sodium hydroxide or calcium hydroxide or cesium hydroxide. All of these contain the OH minus anion, which is referred to as hydroxide. Or they either generate OH minus by reacting with water itself when they're dissolved in water. So an example here is water reacting with ammonia. So ammonia is our base here, and it reacts to generate the OH minus anion in solution. So strong versus weak bases, we can still have some very similar things here as well. Strong bases are strong electrolytes, weak bases are weak electrolytes. We won't really list many examples of weak bases. This ammonia is one example of a weak base, but most of the time we'll stick to strong bases. And strong bases are going to be any group 1 or group 2 soluble metal hydroxide. So it has to be soluble in solution if we're going to use it generally as a strong base in solution, although sometimes you can do things not fully dissolved. But for our purposes, we'll stick to just the soluble cases. So group 1 and group 2 metal hydroxide. So in group 1, that's all of the alkali metals coupled with the hydroxide ion. And in group 2, the soluble hydroxide should be calcium, strontium, and barium hydroxides, and those are listed here. Now let's show a few examples of neutralization reactions in action. So we'll first start with a case where all of the starting materials are aqueous, everything's dissolved in solution. So we'll just take hydrochloric acid reacting with sodium hydroxide. Both are aqueous, so they're fully dissolved, and that means that they're also dissociated into their ions. We form water by combination of the H plus ion with the OH minus anion, and then we're left with a salt, which is a salt we're fairly familiar with, table salt, sodium chloride. To write the complete ionic equation, remember we break up anything that is listed as aqueous. If it's not listed as aqueous, we don't break it up into its ions, but if it is, we break it up into its ions. So HCl becomes H plus aqueous plus Cl minus aqueous. Sodium hydroxide becomes the sodium ion and the hydroxide ion. Water is not listed as aqueous because you can't have water dissolved in water. Exactly, we don't refer to it that way. So it's simply given the liquid phase symbol. So we do not break that up into ions. Sodium chloride breaks up into the sodium ions and the chloride ions. And then to really illustrate what's going on, we look at the net ionic equation, and we do that by identifying our spectator ions and canceling them out. So chloride shows up in the exact same form on both sides of the equation, so we cancel it out. Sodium shows up in both sides in the exact same form, so we cancel it out, and we're left with a net ionic equation that has just H plus, the proton, combining with OH minus to form water. Let's do a second example, one where we start with an insoluble starting material. So here's one where we've got magnesium hydroxide. It's not one of my soluble bases, so I may not refer to it as being a strong base in solution. It's certainly a base, but it will have that start out as a solid, and then we'll add to that a solution of HCl in water, so aqueous. And that will form magnesium chloride and water. And we've got the reaction written in balanced form here. The net ionic equation, remember, we only break up anything that is aqueous. So the magnesium hydroxide does not dissociate because it's a solid. The HCl does because it's aqueous, so you have 2 protons and 2 chloride ions. And magnesium chloride is aqueous, so we break that up into the magnesium 2+ ion and 2 chloride ions. Water is not aqueous, so we do not dissociate it, and it's left as 2 water molecules. Now we go through and we can identify our net reaction by canceling out any spectator ions. In this case, there's only one, which is the chloride ion. That's the only ion that shows up in the same form on both sides. So my net ionic equation becomes simply the solid magnesium hydroxide plus 2 protons going to the magnesium ion plus 2 water molecules. Lastly, let's do an example where we generate a gas out of the reaction. This is fairly common with neutralization reactions whenever we have the carbonate anion or the bicarbonate or hydrogen carbonate anion present. Those will react to form CO2 and water, and CO2 will be given off as a gas. Let's just take an example here. HCl, it's aqueous, reacting with an aqueous solution of sodium bicarbonate or sodium hydrogen carbonate. The bicarbonate and hydrogen carbonate are 2 different names for the same thing. And those are both aqueous solutions. And when we essentially do just a metathesis reaction where you simply swap the anions, we come out with sodium chloride and then H2CO3, aqueous. The thing to point out here, though, is that H2CO3, this is carbonic acid, this is unstable. It breaks down to form water and CO2 gas. So anytime that you would write a reaction out and you form H2CO3, immediately take that and break that up into water and CO2. So we can write out a new kind of full molecular equation where we've got HCl plus sodium bicarbonate produces sodium chloride plus water plus CO2. Now we can write our total or complete ionic equation by, again, dissociating anything that's listed as aqueous. So on the reactant side, everything's listed as aqueous and it dissociates. You have the proton, you got chloride, sodium ions, and the bicarbonate ion. On the right side, sodium chloride also dissociates, but water and CO2 do not dissociate. Water's a liquid, CO2 is a gas, they don't break up. We now can identify any spectator ions, and the chloride ion and the sodium ion are spectator ions here, so we cancel them out, and our net ionic equation simply becomes the proton plus the bicarbonate ion producing water and CO2. And that's how we do neutralization reactions, and things to be aware of when we're writing reactions involving acids and bases.